Greetings of the day to all of you. In the last few lectures, we have studied the isolated DC to DC converters, two types of converter topologies, that is the flyback converter circuit and the forward converter circuit. Now, if we talk about the flyback converter circuit, we know that it can carry only the magnetizing component of current, therefore it is available in very low power ratings, and it is a buck boost derived topology. If you talk about the forward converter circuit, it is a buck derived topology, and it can carry both the magnetizing component of current and also the load component of current, therefore it is available in slightly higher power ratings as compared to the flyback converter topology. But for both flyback as well as forward converters, if you observe their waveforms and their circuits, you see that the current carried by the magnetizing current carried by the windings is unidirectional. It can flow in only one direction. Therefore, the flux is set up in only one direction, and there is unidirectional core excitation. And because the core is excited only in one direction, therefore it is not fully utilized, and both flyback as well as forward converters cannot go into very high power ratings in the order of kilowatts. Although forward converter has a higher power rating than flyback, but if you want an application of the order of kilowatts, then you may have to use a converter that allows bidirectional core excitation, and one such converter is the push-pull converter, which we are going to study today. So let's quickly move to the circuit. We basically have a DC source, and we have two primary windings that are excited by this DC source through two switches. S1 that excites the primary winding N11, that is this winding, and then there is another switch S2 that excites the other winding. Let's call this as N12, and generally we assume that the number of turns of N11 and N12 is say equal to N1, so they have the same number of turns, it's assumed, and they are excited through different switches S1 and S2, which they conduct in different intervals, and this is your source, say VDC. Now these two windings are wound on the same core, and then you have the secondary windings, that is the top winding is, you can call it N21, and it is assumed that it has the same number of turns as the bottom winding, and you can call it N22, and let's say that the number of turns is N2. Now you have a diode here and a diode, an inductor over here, a capacitor, your load, and then the other winding has a diode at the same connection point with LC and R. So again you have two diodes, D1 and D2. So this winding is 1-1, this winding is 1-2, this winding is 2-1, and this winding is 2-2. And you also have an inductor, two diodes and two switches, and this is output voltage of the converter with the capacitor as a filter, and obviously also to take care of the inductive energy. Now we need to see that even if you observe this circuit, you see that when S1 is conducting, your magnetizing current flows through the upper primary winding, and it flows from top to bottom, so you have flux developing in this direction. And when S2 is conducting, you have current flowing down to upwards and flux in the opposite direction. So if you just see this part of the circuit, you know that S1 will cause core excitation in one direction, and S2 will cause core excitation in the other direction. So that's how you are achieving bidirectional core excitation. Now, what is the pattern of conduction of the switches? Let's assume that this is one complete switching interval, say TS, and you divide it into two intervals, TS by 2 and then another TS by 2, so the total is TS, right? In the first half cycle, in the first ts/2, for some duty ratio d, you switch on the switch S1, and then you remove its pulse for the remaining interval. So this is a duty ratio during the first half cycle. And then in the second half cycle, you give the pulse to the other device S2 for the same duty ratio, and then you withdraw the pulse. So your duty ratio over here is T on upon Ts/2. Okay, so you're talking about per half cycle, not about per cycle. And obviously the duration for which S1 is on in its own half cycle is equal to the duration for which S2 is on in its own half cycle. And if you observe, there will be 4 intervals that we will have to analyze the behavior of the circuit for. So you have S1 conducting, S2 conducting, and then their intervals when they are not conducting in each half cycle. Now let's analyze the circuit for each of these intervals. So let's see the first interval, which is 0 to dts/2, when the pulse is given to S1. Okay, so let's see how the circuit looks like. You have your source, the switch S1 is conducting, the upper primary winding is directly excited, so voltage across the, okay, we'll do that later. The other switch is not conducting, but this winding is linked, or they are all on the same core, so the other winding, primary winding, also has flux associated with it. And then you have the secondary windings, and we'll do this later. First, let's see what voltages are induced. Now in the primary winding, the first voltage induced in the upper primary winding is directly VDC, because it is directly connected across the source. The voltage induced in the V12, the bottom primary winding, is equal to number of turns, say N12, upon number of turns of the exciting winding, that is N11, times VDC. Assuming that they are both equal to say N1, so this becomes equal to VDC again, right? So voltage induced in this winding is VDC again. Now the switch that is not conducting, voltage across that switch, if you see, is this voltage VDC plus the induced voltage over here VDC. So voltage across the switch is 2 times VDC. In fact, if you see, this is one of the drawbacks of this converter topology, that although it gives you high power ratings by ensuring bidirectional core excitation, but the devices in this circuit are rated to twice the input voltage. Okay, so the ratings of the devices is higher, and obviously the count of the devices is also more. You have 2 devices instead of 1. Okay, now what is the voltage induced in the secondary winding, say V21, this voltage? It will be N2 upon N1 times VDC, and the dot will be positive, as a result of which it will forward bias this diode, and then energy transfer will take place. The inductor will start storing energy, part of the energy getting into the capacitor and also feeding the load. The voltage on the fourth winding, that is the bottom secondary winding, say V22, is equal to again N2 upon N1. I'm assuming both of these are N1 and both of these are N2, so N2 upon N1 times VDC. But now the dot is positive, this is negative, so this diode is not in conduction. Alright, so this winding is electrically active, it is establishing flux. This winding is also electrically active because it is feeding the load. So the other 2 windings, the bottom 2 windings, are not electrically active, but they are magnetically coupled to the circuit, and they all have the same flux associated with them because they are wound on the same core. And also the primary winding, if you see here in this interval, it carries, say, let's say the primary winding, let's call it I11 over here. So the I11 winding, or you can call it IS1, because S1 is directly connected to the primary winding. So IS1 over here will carry the load component of current, which is, because this is an open circuit, this is the inductor current flowing through here. It will carry the inductor current, the reflected component of inductor current obviously, and the magnetizing current. Okay, so you have both magnetizing current, again, that will contribute to high power ratings. You have the magnetizing component of current, and because the load component is also flowing on the secondary side, so the reflected load component, or which is the inductor current in this case, that is also flowing. In this interval, the current S2, the switch S2 does not carry any current, it is off. The diode D1, the diode D1 is carrying the inductor current itself, because this is open circuit IL, and the diode D2 is not carrying any current, so this current is 0. Also in this interval, this inductor is storing energy, and voltage across this inductor is this voltage minus this voltage, so it is N2 upon N1 times VDC minus V0. And this inductor current is obviously rising, which is this current. It is rising because the inductor is storing energy. Now let's see what happens when we withdraw the gating pulse. In each interval, you can always see the voltage across the non-conducting devices to see their ratings. I have shown it for one switch. You can do it for the diodes as well. And it should also be twice the rating. So this was first interval, all the device currents and the inductor voltage, which was N2 upon N1 times VDC minus V0. Now let's move on to the second interval. In the second interval, we have withdrawn the pulse to S1, and we have not yet given the pulse to S2. So this interval is dTs by 2 to Ts by 2. Now let's see what happens in this interval. Let's draw the equivalent circuit over here. We have S1 going off, as a result of which it appears that there is collapse of flux, due to which a very high negative N d phi by dt spike will be observed in all the windings associated with that flux. So all the dots become negative. So all the dots become negative, whether it's primary or it's secondary. None of the two switches have been given a pulse, neither S1 nor S2. And because this dot became negative, so it looks like that this diode will be reverse biased. And because this diode D1 is reverse biased, therefore it looks like that the current through this inductor, which was previously storing energy, has been interrupted, as a result of which the inductor voltage, which had previously developed like this, will also switch, and inductor voltage will become, it will reverse its polarity. And while reversing its polarity, it will forward bias. Let's see what it will forward bias. One is this diode itself, and the other is this plus sign forward biasing this diode also, and then going on like this. So because your inductor voltage has switched, so this potential becomes a high potential point, positive potential point, and it forward biases this diode as well as this diode by overcoming the potential at the at the windings itself. अब क्योंकि इंडक्टर को एनर्जी, दो तरह के एनर्जी रिलीजिंग प्रोसेसेस को कंप्लीट होना है. एक है कि आपके ट्रांसफॉर्मर के थ्रू एनर्जी रिलीज होनी है, वी विल सी टू दैट ऑल्सो. और दूसरा है कि आपके इंडक्टर के थ्रू एनर्जी रिलीज होनी है. वो दोनों पार्ट्स को इक्वली फॉरवर्ड बायस करें तो दोनों तरफ से वो एनर्जी रिलीज हो रही है. लेकिन जो ट्रांसफॉर्मर की स्विचिंग की वजह से एनर्जी रिलीज हो रही है, वो भी इसी डायोड को फॉरवर्ड करिए D2 को. तो D2 is receiving forward bias from the transformer flux collapse as well as from the current collapse of the inductor, and therefore D2 is going into conduction. And as far as D1 is concerned, it is going into conduction due to the इंडक्टर करंट कोलैप्स. ओके, क्योंकि जो ट्रांसफॉर्मर की वाइंडिंग है वो उसको फॉरवर्ड बायस नहीं कर रही है, ये उसको फॉरवर्ड बायस कर रहा है. फाइन. सो इफ यू सी नाउ all the currents that are flowing into the circuit, the switch current S1 is 0 because it's not conducting. The switch current S2 is also 0. The diode current, say ID1, is equal to, now the inductor is releasing its energy, so IL is falling and we are assuming it's in CCM. So this IL is shared both by D1 and D2. So ID1 is equal to IL by 2 and ID2 is also equal to IL by 2 plus the magnetizing component of current, because we know that the flux collapse जो यहाँ पे हुआ था, जो magnetizing component of current है, अब उसको D2 से जाना है. So this is the magnetizing component of current, reflected of course, flowing through the winding D2. And what is the voltage across the inductor? If we keep up with the old conventions, the voltage across the inductor in this interval, if you see, let me clear this and show it to you. यहाँ पे क्या वोल्टेज इंड्यूस हुई होगी, से n d phi by dt, किक की वजह से, ड्यू टू द फ्लक्स कोलैप्स. एंड हियर ऑल्सो इट इज n d phi by dt. And if you put KVL on this loop, the whole loop, you can simply write 2 times n d phi by dt is equal to 0, because it's a short circuit, right? Basically, you're not allowing flux collapse, right? It looks like that the flux may collapse, but immediately, the circuit behavior is such that something gets forward biased, these diodes gets forward biased, and flux collapse does not happen. So n d phi by dt is equal to 0. And because n d phi by dt is equal to 0, so voltage at these terminals, which is just n d phi by dt between this terminal and this terminal, is also equal to 0. You can assume it to be a short circuit. So voltage across the inductor now is directly equal to minus V naught. Makes sense, because the voltage across the inductor has to be negative for the inductor to release energy, and hence the inductor current to be falling, right? Now if we apply volt second balance, let's apply volt second balance only for these two intervals, because the remaining two intervals will be repetition. अब जो S1 से हो रहा था और D1 D2 से हो रहा था, अब सेम चीज़ रिपीट होगी, लेकिन अब वो S2 से होगी, दूसरी डायरेक्शन में फ्लक्स बिल्डअप होगा और दूसरी डायरेक्शन में कोर एक्साइटेशन होगी. बट the circuit behavior will be symmetrical now, it will be repeat. So हम इन दोनों के लिए ही, if we do the analysis, that is sufficient. So voltage across the inductor is N2 upon N1 times VDC minus V naught for d ts, and then it is minus V naught for, let's call it 1 minus d interval 0. So this is d n2 upon n1 VDC minus dV naught minus V naught plus dV naught is equal to 0. So V naught is equal to n2 upon n1 d times VDC. लेकिन हमने अभी सिर्फ TS/2 तक अपने सर्किट को एनालाइज किया है, या आप ऐसे भी कह सकते हो that your D over here is equal to T on upon TS/2, or it is 2 times T on by TS, जो कि आपका असली ड्यूटी साइकिल है. तो if you put that twice here, where D is the total, the real duty ratio, so it becomes 2 times N2 upon N1 into VDC. Again, it's a Buck derived converter, and you also have turns ratio appearing in the output voltage relationship, so you can have fine control as well as coarse control. Fine control through D and coarse control through number of turns, turns ratio of the transformer to control the output voltage of the transformer. And the benefit that you're getting is that your core will get excited in two directions. We have already done one direction of core excitation through interval 1 and 2, and the remaining third and fourth interval will will help you will make the core get excited in the opposite direction. हम वो भी अभी देखेंगे, and then we can also draw the waveforms. The drawback of the push-pull converter circuit is that one, you need more number of devices. टू, यू नीड हायर रेटिंग ऑफ डिवाइसेस. अगर आप जनरली एक कन्वर्टर में देखो तो आप VDC के इट्स लाइक जनरली VDC की रेटिंग पे आपका बक कन्वर्टर में आपका डिवाइस होता है, बट यहाँ पे ट्वाइस VDC पे होता है. इट्स twice the amount of voltage getting stressed. The same will happen with diodes also. They will also get stressed to twice the voltages. So you need higher ratings as well as higher number of devices in push-pull converter. Now let's see the other intervals, the third and the fourth interval. तो अब क्या होगा, फर्स्ट और सेकेंड इंटरवल हमारा हो गया, राइट. अब थर्ड इंटरवल में don't want to write the inductor voltage right now. We can just do the currents. Yeah. When you talk about the third interval, the pulse is given to S2. So IS1 in this interval is 0 and IS2 in that interval. Now let's see what happens. When you give a pulse to this, I'll not draw the equivalent circuits, but I'll briefly brush through. If you want to do it in detail, I would suggest you to do it on your own. Take a piece of paper and draw the equivalent circuits and, just analyze. When you give a pulse to S2, flux will get established. This dot, current is flowing here, the dots will get negative. So all the dots get negative. The core is getting excited in the reverse direction. As a result, because of the conventions, it's not D1 now going into conduction, but D2 going into conduction. So the current carried by D2, if you complete this circuit, this part, will be equal to the inductor current. So current will flow like this, inductor will store energy again, and then this is the complete path. So again, the inductor D2 will carry the inductor current, which is the diode D2 will carry the inductor current, which is again increasing. And IS2, which is conducting current, will carry the reflected component of this load current plus the magnetizing current. But you must know that the magnetizing current is in the reverse direction, right? So it's carrying current in the reverse direction. What about ID1? ID1 in this interval is 0 because ID1 is reverse biased. ठीक है. अब आप फोर्थ इंटरवल की जब बात करते हो, let's write the fourth interval over here. अब हमने S2 से भी पल्स विड्रॉ की, जिसकी वजह से फ्लक्स कोलैप्स होगा और सब पोलैरिटीज चेंज हो जाएंगी. अगेन द डॉट्स विल बिकम पॉजिटिव. फ्लक्स कोलैप्स हैज अगेन हैपेंड एंड अगेन इंडक्टर वोल्टेज ऐसे बिल्ड हुई थी, इंडक्टर वोल्टेज भी फिर से स्विच हो जाएगी और स्विच होते होते ये इंडक्टर वोल्टेज आपके दोनों डायोड्स को फॉरवर्ड बायस करेगी और इंडक्टर करंट की जो कंटिन्यूटी है वो इंश्योर हो जाएगी. सो बोथ स्विचेस IS1 नो करंट, IS2 again no current, but ID1 and ID2 both are going to conduct and they are going to share the inductor current IL2 by L2. और मैग्नेटाइजिंग component of current को भी कहीं जाना है. Let's see which device will take the magnetizing component of current. If you see the device polarities have changed और जो ट्रांसफॉर्मर वाइंडिंग्स है वो D1 को फॉरवर्ड बायस करी है, ना कि D2 को. सो D1 इज गोइंग टू ensure that flux collapse does not happen. So IL2 plus IM dash is going to be carried by D1. तो अब बस वही चीज़ है, that is the same thing getting repeated as it was happening in 1 and 2, but it's just symmetrically happening with the other devices and core excitation दूसरी डायरेक्शन में हो रही है. If we quickly draw the waveforms for some of these parameters, You have pulse to S1 for dTs by 2, and then it goes off, then to S2, and then it goes off. So this is your Ts over here. So these are the pulses. इंडक्टर करंट की सबसे पहले बात करते हैं. S1 जब कंडक्ट करेगा उसकी वजह से कोर इस्टेब्लिश फ्लक्स इस्टेब्लिश हो जाएगा प्राइमरी में, सेकेंडरी बेस के साथ लिंक हो जाएगी, D1 फॉरवर्ड बायस हो जाएगा, इंडक्टर एनर्जी स्टोर करने लगेगा, फिर इंडक्टर एनर्जी रिलीज करेगा दोनों की तरफ से, इंडक्टर करंट विल फॉल, फिर से आप दूसरे स्विच को ऑन करोगे, इंडक्टर फिर करंट इसी डायरेक्शन में, इंडक्टर की एक्साइटेशन एक ही डायरेक्शन में हो रही है, ट्रांसफॉर्मर कोर की एक्साइटेशन रिवर्स हो रही है. सो इंडक्टर अगेन इट्स गोइंग टू टेक करंट, अगेन दैट करंट इज गोइंग टू फॉल. सो एक स्विचिंग साइकिल में 2 बार आपका इंडक्टर एनर्जी स्टोर और रिलीज कर रहा है, बिकॉज यू हैव 2 स्विचेस. सो दिस इज योर इंडक्टर करंट. नाउ लेट्स डू द current through S1 and the current through S2 and the current through diode D1 and the current through diode D2. So when S1 is conducting, what component of current is it carrying? It is carrying the magnetizing component of current and the reflected load component. So S1 is carrying IL dash plus IM when it is conducting. Then the pulse is withdrawn and the pulse remains withdrawn, so no current will flow all the way till Ts. ठीक. अब हम IS2 बनाते हैं. IS2 को सिर्फ कंडक्ट करना है जब S2 को पल्स मिलती है, उस टाइम पे भी इट विल टेक up the inductor current, that is this current, plus the magnetizing component of current, that is IL dash plus IM. इसको हम पॉजिटिव ही बना रहे हैं क्योंकि डिवाइस करंट है. इट्स नॉट, इफ यू ड्रॉ फ्लक्स की डायरेक्शन दैट विल रिवर्स, बट वी आर टॉकिंग अबाउट द डिवाइस करंट विल बी स्टिल पॉजिटिव. फ्लक्स की डायरेक्शन इस केस में पॉजिटिव होगी और इस केस में नेगेटिव होगी. सो डोंट कंफ्यूज द टू थिंग्स. देन लेट्स ड्रॉ ID1. Diode D1 in the first interval is conducting, because switch is conducting, this is positive, and it is carrying the inductor current itself, right? And then once it switches, it will carry, this becomes negative, it will carry only IL by 2. So this is a current carried by, this is IL and this is IL by 2, right? और अगर आप ID2 की बात करो तो इस इंटरवल में पहले ID2 0 है एंड देन ID2 इज IL by 2 प्लस IM डैश, राइट? ओके. अब जब हम S2 को पल्स देते हैं तो S2 को पल्स देने की वजह से आपके डॉट्स जो हैं वो सब नेगेटिव हो जाते हैं, बिकॉज करंट फ्लोज लाइक दिस, ऑल द डॉट्स आर नेगेटिव. So that time you do not have D1 going into conduction at all, so your D1 becomes 0, D1, no current flowing through D1, but D2 is definitely carrying current. And what current it's carrying? It is establishing, it is carrying the inductor current itself. तो जो भी इंडक्टर की करंट है वो आपकी सारी की सारी ले रहा है D2. So this is your IL being carried by D2. पहले इंटरवल में D1 लेता था, अब D2 लेगा, ठीक है? And then when you withdraw that pulse, this all the dots again become positive. They will switch polarity. The inductor will also switch polarity. और इंडक्टर की पोलैरिटी स्विच होने की वजह से क्या होगा कि दोनों डायोड्स में इक्वली हाफ्स में करंट इंडक्टर की डिवाइड हो जाएगी, और जो आपका D1 वाला डायोड है, दैट D1 वाला डायोड जो है वो आपका फ्लक्स मैग्नेटाइजिंग कंपोनेंट ऑफ करंट भी लेगा, बिकॉज ऑफ द पोलैरिटी ऑफ द बिकॉज ऑफ द डॉट्स की जैसे पोलैरिटी इस्टेब्लिश होगी. ओके, सो नाउ वी आर टॉकिंग अबाउट दिस इंटरवल. D1 is carrying IL by 2 plus IM dash, and D2 is carrying only IL by 2. So if this was IL, now it will carry only IL by 2. Previously, in the previous half cycle, it was taking the magnetizing component of current as well. So basically आपने number of devices बढ़ा के अपनी core excitation को दोनों डायरेक्शन में पॉसिबल करवाया है, जिसकी वजह से आपने कोर को बेटर यूटिलाइज किया है, बट एट द कॉस्ट ऑफ इंक्रीजिंग योर डिवाइस काउंट एंड इंक्रीजिंग द रेटिंग्स ऑफ द डिवाइसेस. And you have achieved bidirectional core excitation, so higher power ratings are available, and you have used multiple windings, and you have ensured कि आप दोनों डायरेक्शन में अपने कोर को एक्साइट करो. सो इट्स जस्ट पहले 2 साइकिल में एक तरह से कोर एक्साइटेशन होती है थ्रू S1, और फिर जो आपके डायोड्स के बिहेवियर होते हैं, उनके करंट्स लेने का टेंडेंसीज होती हैं, वो सेम चीज़ रिपीट होती है बाकी 2 इंटरवल्स में जब S2 कंडक्ट करता है. इट्स जस्ट दैट बिकॉज ऑफ द पोलैरिटीज गेटिंग चेंज्ड, देयर रोल्स गेट interchanged. So just try to draw these waveforms. It slightly appears to be a little tricky, but it is not. If you draw these waveforms and draw the equivalent circuits, you can, in every interval, you can write their current sharings, and then you can simply draw them from one. If you draw it like a table, and then you can draw it from there, it will be very easy for you. So with that, we finish isolated DC to DC converters. There are other isolated DC to DC converters also, like the half bridge converter and the full bridge converter, which are again similar to push-pull converter. They allow bidirectional core excitation, but they are for you as an assignment because they are very similar to this converter. बस उसमें ratings devices की इतनी ज़्यादा नहीं होती हैं, but they also allow bidirectional core excitation. So with this, we finish module number 2 for MTech, and we will now move on to voltage source converters and their modulation techniques from the next lecture onwards. Wishing you all the best, and if you want some lectures on numerical problems, we can also have a Google class for that. I mean, on Google Meet, I can share some problems with you. You can try it over a week, and by the end of the week, we can just discuss those problems on a live session. That's all for today. All the best.